Hi Wildcats, this is Unit 2, Focus Question 2, where we will be looking at waves interacting with other waves. So, if you've ever been on the beach, you might have observed that when waves crash into each other, they behave a little differently than any one wave individually. Like in this picture here, right? So we've got two waves, they're crossing paths, like maybe from the boat, two boats, and they make this little spike. Or something else you might have observed is if you're in a room that has multiple speakers, depending on where you stand, you might notice differences in volume in that room. And that is because those waves, whether it be sound waves or ocean waves, are interacting. And so in this focus question, we want to look at how do waves behave when they interact. Okay, so a great example is an echo, right? You stand here and you clap or you yell and you hear it back. And so what's happening is waves are able to reflect or bounce off of objects. So in this case, these are sound waves. They travel this direction, bounce off the wall, and then travel back where they can be heard. And so that's really all an echo is you are hearing the sound waves that came out of your mouth travel and then reflect off a wall and then bounce back and then your ears pick them up. So, the big thing to understand about wave reflection is that when we send waves, or when waves are sent or travel, they can bounce back or reflect. And that's what we see here with like a wave. If we took a string or the spring and sent a wave and tied it to something, it'll travel down and then it travels back. And we saw that in the hall when we were playing with the snaky springs out there as well. Okay, so let's start by looking at what happens, how waves reflect based on what kind of boundary they bounce off of. And so the first is called a free boundary. It's called a free boundary because it is, well, it's free to move. So in this case, like here is a rope, but it's tied around instead of tied onto this. So this rope could move up and down. We did this in class where the metal poles that we have the springs on, it would be like you're not holding on to it, so it can bounce around on that metal pole. And what we observe is that the wave is reflected. I don't really like upright here. So I think what we see first is that first the wave is traveling left to right, it bounces off here, and then off this free boundary, and then it returns traveling to the left. What we notice then is if we're going to call this 0, this position 0, then we could say that this has a positive, since it's above 0, a positive amplitude. When it comes back, it also has a positive amplitude. Okay. So when we say the wave is reflected, we would say the wave is reflected with the same amplitude that it went in with. So a positive amplitude is returned with a positive amplitude. The other thing, when it says amplitude remains the same, what really we're saying is energy remains the same. Now, you got to remember this is in physics world. We're going to ignore things like energy loss. In reality, energy is lost to the spring or to the rope, to heat, and all those little things, but it makes our complications far more complicated. So we're going to pretend that energy is never lost. And that means that if I were to measure this amplitude and say have +1 meter amplitude when I sent it, then when it reflects back to me, it's still going to have +1 amplitude. And so you can see that here. The opposite would be true. If I sent a wave with a minus amplitude to a free boundary, so this is -1 meter, when it's on its way there, it's got -1 meter. When it comes back, it would have -1 meters of amplitude as well. So it reflects in the same way that it goes in. On a fixed boundary is one that can't move. So in this case, we would tie this rope to this pole, so it's not allowed to move up and down. And what we see is when it goes in, so it's going in left to right, it has a positive amplitude. On its return, or when it's reflected, it has a negative amplitude. So it is reflected in the opposite way. The amplitude does stay the same because we're assuming no energy loss. So if this is +1 meters on the way in, then it would come out with -1 meters. And you can see that here too. It reflects off of this boundary, which is fixed, and comes back and it has flipped amplitudes. So on fixed boundaries, the amplitude of it is flipped. On free boundaries, it stays the same. Okay, so now that we see how they can reflect, let's look at what happens when we send more than one wave or more than one wave is on that rope. So the This is called superposition. Matter can't be in the same place at the same time. That's what makes bumper cars fun. This would be a lot less fun if the car could just drive through each other. That's not how it works. Matter can't be in the same place at the same time, so there's no way, so these objects bounce off of each other. Energy is not matter. So therefore, energy moves through matter. So as a result, waves, which are energy, can move through each other. Sound waves can move through each other. It would be like, it wouldn't make any sense if we shot two speakers at each other of sound and they bounced back. The sound like stopped and bounced back. That's not how it works, right? You can see in this picture of waves, if I drop two rocks in the water, the waves don't bounce off of each other, they move through each other. And the same thing's true with sound. So these areas where the waves are on top of each other, right? They're overlapping. That is called superposition. Okay, so that's superposition. Um, Also note, there's a separate video where I do a talk through kind of on superposition with a simulation going. So if you're a little unclear on what superposition is, you might check that out in the learning resources. It's kind of just hopefully a way to clarify what happens when waves overlap. Okay, so there's two things can happen when we have superposition. The first is constructive interference. So constructive interference occurs when pulses have the same direction or they are in phase. So in other words, if I sent two waves and they have the first wave has positive and the other wave, they both have positive amplitudes, they would constructively interfere. The same would be true if they both had negative amplitudes. They would be in phase, so they would constructively interfere. So what does that mean? What it means is that they add together. They construct, right? The root word of constructive is construct. So they add together. So in this position or picture, I have a wave that has a positive 4 amplitude moving left to right and a plus 2 amplitude moving right to left. And when they get to the same portion of the rope, they add together. And what I observe is a wave that has a positive 6 amplitude. Because waves don't, they can move through each other, then they pass through each other. And so now the plus 2 wave keeps going to the left and the plus 4 wave keeps going to the right. So they move towards each other, interact where they add together or construct, then pass through each other and then go on their way. And so that's what you see here. You can see these two waves, A and A, when they are combined, we get 2A. And so this explains why if I have two speakers playing, right, two sound waves traveling like this from a speaker here and a speaker here, and they go towards each other, then when they are overlapping in this area, like right here, I have its loudest because the wave has the biggest amplitude, right? This is a plus 2 coming, let's say, an amplitude or volume of plus 2. This is an amplitude or volume of plus 2. So when they're overlapping, I have a volume of plus 4. In other words, they're louder. Okay, so that's constructive interference. The other type of interference is destructive interference. Destructive interference is when I have two different waves. So for example, a wave with a positive and a wave with negative amplitude together. And what destructive, right, root word, is destruct or destroy. So they cancel each other out. They still pass through each other, but they cancel each other out. So in this picture, I now might have a plus 4 traveling towards a minus 2 amplitude wave. So when they meet, plus 4 minus 2 means that they cancel the minus 2 cancels the plus 4 to some degree, and I end up with a smaller wave, a plus 2. Yet again, they pass through each other and then travel on their way. And so this is when they're different. But in this picture over here, I have A and minus A. And because they're the same amplitude, or because they're both the same magnitude, but different directions, right? This is plus A, and this is minus A. They're the same. So, well, let's just give it a number. We'll call this plus 1 and minus 1. Well, when they overlap, what's plus 1 minus 1? It's 0. So this is actually a picture of two waves moving through each other. It looks like there's no wave there because they are canceling each other out. And so there are areas, there are areas where in like music halls and stuff where you can't hear things as well, and that is sometimes by design and sometimes by accident where the sound waves meet and cancel each other out because of how they are overlapping. Okay, so we have constructive and destructive interference along with different types of reflection. Let's put it all together, and when we do, well, I guess I'm getting ahead of myself. Here's an example, so we could do this together. You might want to pause this for a second, see if you can do these. So what do we have? I have +3 and +1. So when I do that, those waves overlap, and I would end up with a wave that is bigger. So this would have a +4. Here I have +3 and -1. So then I would end up with a wave that is smaller, and this would be -2. Okay, so hopefully that went well for you. We can see here, this is what they look like when they're overlapping. I also have 2 videos on these as well, so if you wanted to see constructive and destructive interference, there's additional resources on the learning resources. But here you can see the red wave and the black wave overlap. So I've got +3 and +1, which means they add together. Over here, I've got +3 and -1. So with this region right here, they would cancel each other out to some degree, which means I get a smaller wave in its magnitude. Okay, now let's put it all together. And that's standing waves. So what happens when, instead of just sending one wave down a string or a rope or a spring, I keep sending multiple waves? Well, when I send my first wave, it's going to travel down this rope and it's going to reflect. And so now it's coming back. On its way back though, I keep sending waves down here. So now as these waves are bouncing back, I'm sending more waves towards them, which means they're going to start to constructively and destructively interfere because they're reflecting off of this boundary and interfering with the waves coming towards them and bouncing back and forth, back and forth. And what happens is you get these things called standing waves. They're called standing waves not because you do them standing up, but because they look like the wave isn't moving. So in this picture, this rope is moving back and forth, back and forth, back and forth. It is moving, but it looks like a permanent wave because, or a standing wave, because of the constant constructive and destructive interference. This happens when waves that have the same frequency, wavelength, and amplitude, they all have to match, are reflected back at each other. And those interacting waves create those patterns of constructive and destructive interference. Okay, so couple things. One, there is another video on standing waves as well. So if you want to see those in action, you can see that. We're going to work with them in class coming up. Some things you need to know about standing waves. There are 2 regions, nodes and antinodes, which seem to be named backwards, but this is just the way that it is. Okay, nodes are where we have complete destructive interference. So nodes, I remember it as no. There's no wave there. This is a node. This area right here is occurring because this first wave and second wave that's bouncing back and interfering with each other are canceling each other out. So the waves here would be like +3 and -3. So therefore, there is 0 wave here. This is called a node. Antinodes, which again seem weirdly named, are where I have complete constructive interference. So in this case, the +3 wave is interacting with another +3 wave, giving me the largest possible amplitude of, say, 6. Okay, of +6. And so antinodes are the area where I have constructive interference, and nodes are the regions where I have destructive interference. Okay. Whew, here we go. Standing waves can be used to measure the wavelength of a wave because I can count nodes and antinodes. So in one full cycle, right, well, let's just look at this. Here, I start here, so one full cycle would be from here to here and back. So that would be one wavelength or a complete cycle. That means I'm going to have a node, an antinode, a node, an antinode, and a node. Every wave is going to have that repeating pattern. Okay, so if I can count node, 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 3 nodes, I know that the distance between this node and this node has to be one wavelength. Okay, this is obviously another cycle over here, so we could look at 2 wavelengths. Okay, so one of the reasons we look at nodes and antinodes is it allows us to easily measure the wavelength, which is something that we'll do coming up. So Here are some pictures of different waves I could make, right? So this would be half a wave. Well, how do I know? Well, because there's not, I'll use a different color. Here's a node, here's an antinode, and here's a node. Well, we said on our last slide, I need to go node, antinode, node. This is half a wave, antinode, node to get back to a full wave. And in this picture, we can see I haven't done that yet. I've just got half of a wave. So just by seeing two nodes, I know that I have two nodes slash 1/2 of a wavelength. In this picture, I have that full cycle in this standing wave. So here to the node and then back. So that would be one full wave. 1, 2, 3 nodes. Here I have more than that. I have 1, 2, 3. So this is one full wave plus another half. Okay, because I get to another node. I have 1, 2, 3, 4 nodes. Okay. And so hopefully this gives you a little idea of how I can use counting the number of nodes to determine how much of a wave or how many waves I'm seeing there. That means I can do math, which I'm sure you love, because I can calculate a wavelength just by counting the number of antinodes. So in this picture, how many antinodes do we have here? Well, I have one antinode, two antinodes, okay? Or 1, 2, 3 nodes. But we're focusing on antinodes. So here's 1, here's 2. Well, I have two antinodes, and I know the string that I have those antinodes standing on is 2 meters. So if I take 2 times the length of the string divided by the number of antinodes, I get the wavelength, and that is 2 meters. On this last picture, we just looked at this. So if this string, we said this is one wave. So if I told you this string is 2 meters long, you would say, well, then one wavelength must be 2 meters. That's good. And that's exactly what the math told us here. This becomes more complicated the more and more wavelengths I have on my wave. So in this case, I'm counting 1 antinode, 2, 3 antinodes. So, and the string remains 2 meters. So now I'm taking 2 times 2 meters divided by 3. I have 1 1/3 meters, which means this is one cycle. So if this whole string is 2 meters from here to here, I'll use a different color. This right here, which I can see just by looking at it, is one full wavelength. That must be 1.3 meters long. Okay, that's it. There are some practice problems. I hope that helps. You can walk through those practice problems. We can go over them in class as well. And yep, we'll do some practice with this because coming up when we get to focus question 3, this is going to help us determine some things about not only wavelength, but frequency as well. So I hope that helped. Use the other resources and videos as well if you would like some additional support on this.